Okay, well, thank you for the introduction. Thinking back to when I was an early graduate student in the early 1970s, we basically knew practically nothing about the planets. We knew Venus was kind of a little yellow ball out there, and there were some radio telescope observations suggesting maybe it was hot at the surface. There were a few spectra, there was a little water there. The outer planets, Jupiter and Saturn, obviously Saturn has rings, and they all have a bunch of moons. But basically, are just little striped balls you could barely make out in the telescope. Mars was a little bit better, but not much. It was kind of a fuzzy thing, you know, with little splotches on it. Splotches kind of change darkness every once in a while. We knew it had polar caps. We knew there was CO2, despite the fact that every recent mission goes out looking for water. We've known there's water on Mars for decades. So we knew there was water on Mars and also carbon dioxide. So we knew a little bit about Mars. But as a graduate student at that time, it was kind of disappointing because the first flyby of Mars, whipped by the planet, a couple quick pictures, and all of a sudden was some craters. And I can remember reading when I was about a second-year graduate student in the physics department, a book by Bruce Murray, who was later director of JPL, saying it was a waste of time to even go to Mars, and at this time made a spacecraft on the way, because it was just like the moon, and there was nothing there, and I counted craters. So the spacecraft got to Mars, and looked down on Mars, and unexpectedly couldn't see anything because there's a global dust storm. And they sat around and waited for a while, and finally the dust started to settle out. Two big volcanoes came popping out of the top of the dust, these circles. Eventually the dust cleared, and sure, there were craters there, but there were also things like this river here. So you can see flow features here, like this teardrop shape behind this crater. The water has been flowing down this channel at some time in the Martian past. So we've known about this for 30-something years, and we still don't understand it, which is the point of this talk. So how do we understand the origins of these rivers, and how do they fit in with what we know about the Earth and what causes climate changes on the Earth? So current Mars is a cold, dry place. It's colder than Antarctica. It's about the same as the Antarctic stratosphere in the wintertime, pressure-wise, water-wise, really cold, and very little pressure. If you stepped out on the surface, your blood would boil from the low pressure, which you'd freeze to death and slowly be killed by particles. So not a great place for living at the moment. There are lots of features on the surface. These are 3 of the largest volcanoes in the solar system, the biggest ones around on the other side there. This is a big Grand Canyon, which is long enough to stretch across the entire United States. So there's a lot of interesting geologic features there. We've known for decades that water is present. So when you look at Mars, you can see these bright polar caps, even with a small telescope. And they come out and go back with the seasons as carbon dioxide in the atmosphere condenses on the surface, sort of like automatically going from Florida to the top of Boulder or something like that, just because the pressure in the atmosphere is fluctuating up and down in time. But these are carbon dioxide, dry ice. But here are a whole bunch of water clouds, which you can see in the atmosphere. So we've known for a long time that there's water there. Recently, quite a few orbiters in orbit around Mars now. Some of them are very high resolution. And so this is part of some data from the Mars Reconnaissance Orbiter, in which they found 65 craters that had been formed on Mars since the thing had been put in orbit. So there are 65 craters formed in a few years that this thing has been in orbit around the planet. And this is one of them. It's about 20 feet across and 5 or 6 feet deep. And you can see when this little thing hit the surface, it brought up all kinds of ice that was obviously just below the ground there. And here it is a few months later, and you see the ice is evaporating rapidly away. So there's clearly ice just below the surface over much of Mars. We've been able to map this with other instruments that are less tangible than craters from space, and pretty clear that there is widespread ice on Mars and thick layers under most of the crust, particularly at higher latitudes. Now we know that you can get liquid water on Mars even now. I don't quite understand how, but but we can see things. Here's an ancient river valley, and on the slopes of the banks of this, as well as in these craters, there are things coming down the walls like this, which are called gullies. There probably are places where water is come rushing down the sides of this slope here. At the bottom, you can see a sand dune. That's what this crinkly stuff is. So people think these are pretty young because they go underneath this sand dune, and the sand dunes are moving around in moderate periods of time. So these probably formed in the last few million years. And you see many of them only get partway down the slope, which suggests that the water that came out somehow from up here couldn't get all the way to the bottom before it disappeared. And this is an interesting physical phenomenon, which you can see if you can bring the air pressure down to Martian pressures, which are below the triple point of water. So on Mars, most of Mars, water is like carbon dioxide in the Earth. It can't exist as a liquid. And if you throw liquid water out into Mars, it simultaneously boils and freezes. So it's a kind of an odd thing to think of water boiling and freezing at the same time. That's probably what happened here is the water came rushing out and it's boiled and froze. And by the time it could get down to here, it turned into a chunk of ice and evaporated, and so it never got to the bottom. So anyway, you can get water now. So this is obviously very interesting. I'll give you my idea of where this came from a little later on, but that's not what we're really interested in here. We're interested in river valleys. So these are distributed in a non-uniform manner over the surface of Mars. And you can see there's two kinds of them here, yellow ones and red ones. So the red ones are what people call outflow channels. I'll show you a picture of that in a second. And these yellow ones are the valley networks. So the red outflow channels are probably mostly being caused geologically by heating of the subsurface. So not very interesting to an atmospheric scientist. But valley networks look like they form from rainfall. And you can see here that a lot of the outflow channels are up here in the northern hemisphere of Mars, which is young, low wide. And whereas these outflow channels are mostly in the old cratered uplands of Mars, some exceptions, these are much older than these red ones. So here's an example of an outflow channel. So over here on this side, there's a kind of a source region here. There's another source region down there. And water evidently came flowing out here and then down this channel and carved some little islands down here and spread out into this plain. And if you look at the head more carefully, which you can see up here, and it appears what happened here is that something warmed the subsurface, and the water was melted and came rushing out in some sort of a flood event, and went down this plain and evaporated. So this is typically what these things look like. A lot of them are on volcanic provinces, so they're probably being heated by whatever caused the volcanoes. They suggest that there are groundwater sources there. Here's a picture of another one. You can see this kind of weird evacuated place where water came flowing out of at some point in Egypt and Mars. Okay, the valley networks are the ones that I'm interested in. So some of them are really long, like here's one that's several hundred kilometers long. As you can see, it has little tributaries up here, so the water is flowing that way. So tributaries join together to make this larger river. Many of them are not that long. There's a 30-kilometer mark. You can see this whole surface is just a whole network of tributaries all feeding down into this channel. This is a kind of a more typical situation where there's a big system of tributaries that are feeding the river. So this wide distribution suggests that this is something that's caused by rainfall. You can see them on this one, but lots of these things aren't very big. So here's one with 3 or 4 tributaries going down there, and some more of them over here. So these things are all over the planet, the oldest parts of the planet. Okay, so rivers are not the only thing that's distributed non-uniformly. Craters are also distributed non-uniformly. So these are the 145 craters that are easy to see that are larger than 100 kilometers in diameter. There's probably twice as many as this, but they're buried up here under this dust in the northern hemisphere, so it's hard to count them without going to extreme efforts. Some of these are pretty big, so here's Hellas, which is about 2,000 kilometers in diameter. Isidus, which is also about 2,000 kilometers in diameter. And Argyre, which is about 1,000 kilometers in diameter. So Argyre is going to be the hero of my story this evening. If you look at these, you can see that there are all these craters, pretty much all the craters around this old southern hemisphere terrain. And old means there's a lot of craters on it. So that's what old means to planetary people, lots of craters. And because there's not many craters up here, it's young. So that's what time means on a planet like Mars. We don't have any other way of dating it except for the meteorites that come from Mars. So we date it by counting the craters. And you put this together. So now the rivers are here in yellow or red, and this kind of greenish color. So it's pink color has the most craters on it. It's the oldest. And then this is kind of the next oldest, and then all this bluish stuff up here is young. So we can try to date the rivers with the craters. And a little later I'll show you could even date craters with craters, so we can get an idea of how old both the craters and the rivers are. So here's the average age of the valley networks. So these are valley networks in blue. And these red ones are some of those outflow channels. There's more than one dating scale here. This one's the most compressed one. If you use the alternative dating scale, then this crater here, instead of the river valley, instead of being 3 billion years old, is about 1.5 billion years old. So you can really expand these ages over here. But both scales pretty much agree that the networks, the river valley networks, are around 3.8 billion years old. So they're quite old features on the planet. You can see that it doesn't make too much difference how long they are. They're all still clustered around the same ages. So there doesn't seem to be a particular pattern. And the meaning of these ages is that this is the last time that water flowed down the river. So it's not the time when the river formed necessarily, it's the last time water is flowing down. Okay, so how are we going to explain these river valleys? So in the 1970s, I tried to explain this along with Hugh Rash and Carl Sagan, and people at that time had just noticed that the ice ages on the Earth, we're in an ice age now on the Earth, because we have ice on the polar caps, which is not the normal state of the Earth. Only about 10% of Earth history has polar caps. So we're in an ice age now. And the ice is coming and going. It was over Chicago, a mile deep, 10,000 years ago. And probably 100,000 years from now, we'll have another ice age, but it doesn't happen sooner. And that seems to be driven by changes in the axis of the planets. So there are three different components of the axis of the planet. There's the eccentricity of the orbit. So the Earth has a very circular orbit around the sun. Mars is kind of eccentric. And right now what that does is make it warmer in the southern hemisphere summer. The Earth has only a modest eccentricity. Something like half of the students at Harvard think that the summer is because Earth is closer to the sun in the summer. It's closer to the sun in the winter in the northern hemisphere, so that doesn't work. The second thing you can have is the tilt of the axis, the spin axis of the planet to its motion around the sun, which is what causes the seasons. So we just passed the equinox when this tilt was aligned with the orbit, and right now the northern hemisphere is starting to tilt away from the sun, and so the sun is moving down here, and it's normal below the equator, and starting to get winter. And obviously, if you increase this angle, you can make the seasons more extreme. Well, on the Earth, this angle is about 23 degrees, and it bobs up and down by about 1 degree, which is probably the principal driver of terrestrial ice ages. On Mars, the angle currently is about 25 degrees, pretty Earth-like, And we think it bobs up and down by about 10 degrees, and may change by even more than that. So the Martian orbit, this element of it, is extremely unstable. This is because Jupiter is sitting there tugging on the planet, and it's like you've got a spinning top, and spinning at some angle, and you keep pushing and shoving on it, it's going to start bobbing up and down. The Earth gets tugged as well, but because we have a moon, which is an accident, because we have the moon, it damps that oscillation, and we don't have this big variation in this angle. So anyway, this angle changes a lot for Mars. And then we have the precession of the equinoxes, which basically changes what season the planet is closest to the sun. Okay, so there are things on Mars that are almost certainly due to these orbital changes. So if you go to the polar regions, there are these big stacked plates. So here you can see these stacked layers. Each one of these is about 10 meters thick, 30 feet. And they're very extensive. In the polar regions, there's a huge amount of mass in them. They're probably mostly water ice with some dirt in them. And then here's part of the ice sheet on the top of that. So these things are almost certainly being caused by these orbital changes. This kind of looks like going to Arizona, looking at the Grand Canyon, where you can see all these different layers that represent different local climate changes. In this case, though, they're probably being caused by the atmosphere. The planet tilts to the sun, all the atmosphere comes out into dust storms. When the pole tilts away from the sun, all the atmosphere condenses on the pole, and nothing happens for a while. So you get different layers forming that way. You even get layered terrains in the tropics. Here's some craters. And you can see how these craters have been filled in, probably with dust and other things, this nice layered structure. So this layering certainly indicates climate change is going on the planet. And at first we thought this was going to solve the river problem, and all we had to do was wait 20 or 30,000 years, and the rivers would come back. But as I showed you a few slides ago, the rivers are 4 billion years old. So that didn't work. And here's the period of the obliquity. So you can see this thing is tilting up and down. Here's 10 million years. And this is the tilt of the planet. It's tilting up and down a lot, even more in the past. But it's doing it on something like a 50,000 year period, tens of thousands of years. Totally the wrong time scale. So that idea wasn't it. We tried a parallel there between the Earth and Mars. Didn't work. Okay, so what can you try next? So this is what people have been trying for the last 35 years. So we tried greenhouse gases. They have been important in the long-term evolution of the Earth. So this goes by a lot of interesting names like faint young sun problem, Goldilocks problem. It's also related to the habitable zone about other stars. I'll get to the faint young sun problem in a moment, but the Goldilocks problem is, well, these planets are all kind of similar. Venus is too hot, Mars is too cold, the Earth is just right, which is why Goldilocks is drinking that soup. So how is that? Why is the Earth so lucky? And so we managed by the middle of the 1980s to concoct a really great story about this, which seemed to fit in for all three of the planets. Which unfortunately has unraveled in the last decade for all three of the planets. But nevertheless, it's still what the majority of people think. So here's how you're supposed to imagine this for Mars, that you're on ancient Mars, and there's this giant volcano off in the distance, and it's venting gases to the atmosphere, carbon dioxide, sulfur, and these gases are making a dense atmosphere like Earth's, instead of the puny atmosphere that Mars has, which is like being more than 30 kilometers up in the atmosphere of the Earth. All those gases are the greenhouse gases are heating the surface, freeing all that water that's buried under the soil to make lakes and rivers. So that's the concept here that people have at the moment. Okay, so what's the faint young sun problem? So I should say that, if this is all that went on, we wouldn't really have a problem here understanding how to make Mars warm. Because Venus, for example, this is a surprising thing that people don't observe. Although Venus is half of Earth's distance to the sun, so you would think it's getting more sunlight. In fact, it has these highly reflective sulfuric acid clouds. So really, Venus gets only a little bit more sunlight than Mars does, because it wastes it all by reflecting it back to space. But Venus has 100,000 times as much carbon dioxide in its atmosphere as the Earth. Its temperature is the same as a self-cleaning oven. So all you have to do is ramp up CO2 to some huge amount, 100,000 times, and you can make any planet hot, more or less. So Venus shows you could do this if you put enough CO2 in the atmosphere. And so for a while, we all thought that was going to work out. But then various problems got in the way. So there's something called the faint young sun problem. So the problem with the faint young sun is, okay, so we have an axis here, which is the temperature of the planet, and this is the solar luminosity. And so here we are at the present day. Go back to 4 billion years ago, the sun was only about 75% as bright as it is now. So very people are trying to find ways around this and go look at other stars that are like the sun. It seems like this is just a fundamental part of converting hydrogen to helium in the interior of the sun. It seems to be unavoidable. Other stars like the sun do it. So this causes quite a problem for the Earth. If you take the Earth's current atmosphere and you keep it the same and you keep going back in time, then the Earth should have been frozen over 2 billion years ago. But you know the Earth wasn't frozen over 2 billion years ago because we can find evidence for water. The water back here below 4 billion years ago, and the origin of life in the oceans about 3.8 or so billion years ago. So that's the problem. The sun was less bright, but we know that the planet wasn't any colder. And we still get the same problem on Mars. Mars was apparently warmer in its past when the sun was less bright. So this is, going in the wrong direction. So how do we solve this problem? So people tried to solve it with carbon dioxide. So the logic is Venus is really hot because of carbon dioxide. The Earth has got just as much carbon on it as Venus does. We just have it in limestones. So take some amount of limestone, put it back in the air, you can warm up the planet. So this is how much carbon dioxide you need going back into the past to warm the planet up. So we're starting off down here, present time, at a few hundredths of a percent. If you go back here to the time of the dinosaurs, maybe you need a few tenths of a percent. If you go back here to 2 billion years ago, when oxygen started to rise in the atmosphere, now you're starting to need about 10%. And if you go back here to 4 billion years ago, you need an atmosphere which is dominated by carbon dioxide. None of this is impossible if you think about the cycle, but there are a few data points, such as this one here, which you can see is almost 2 orders of magnitude too low to make that work. So that threw a little monkey wrench into this problem, which of course people had no problem getting around. They stuck other gases in the atmosphere, but nevertheless it messed up a nice straightforward carbon dioxide story for the Earth. Okay, so here's the Goldilocks solution that was so nice in the 1980s. So basically, this is a volcano over here, putting out stuff. And here's some weathering going on here in Boulder and the mountains. And here's a seafloor. The ocean seafloors in the Earth are only tens of millions of years old. Every few tens of millions of years, all the ocean floor is sucked underneath Sumatra and Samoa and those places that have had numerous earthquakes in the last few weeks, in the trenches in the Pacific there. So what happens here is there's a lot of carbon-rich material down here that's melted, and the carbon dioxide comes out into the atmosphere, and then the carbon dioxide gets into water, right? Water clouds, lowers the pH, makes the water slightly acidic. So pH of rainfall is about 5 if it's not diluted because of the carbonic acid, like Pepsi. Anyway, so that acidic water then falls on the Rocky Mountains, Himalayas, and it erodes silica from the mountains, but it also erodes calcium from the mountains, which flows into the ocean, and then the calcium combines with carbonate that's in the water from the CO2 and makes limestone. So this is a nice cycle. You see, it goes around and around and around. And so it can either be in a steady state, maintain things the way they are, but there's also various ways to upset this. If you go back to the early Earth, there's probably more volcanic activity. You probably put more CO2 out. There weren't as many continents, so you probably took less CO2 out. So that's how you justify ramping CO2 up in the early Earth's atmosphere. On the other hand, if it gets too warm and you get lots of weathering here, that'll make a lot more limestone, that'll pull the CO2 down. And if it gets too cold, you won't have any weathering and the CO2 will build back up again. So, for example, that's how the Earth recovered from the snowball episodes. There were several times in Earth history when the whole planet entirely froze over. And the way it got out of that was the weathering stopped over here because there wasn't any rainfall anymore, just snow. So we stopped weathering this, and the volcanoes kept going, and it pumped the CO2 up enough to get us out of it. At least that's one of the current stories for that. How does this fit in with Mars and Venus? Well, on Venus, it's just plain too hot to get any rainfall, so that part's broken over there. The volcanoes have pumped all the CO2 out into the atmosphere, and you've taken all the Earth limestones, melt them all, you shove them all out through volcanoes, you get 100,000 times as much CO2, which is what's in the atmosphere of Venus. What happened to Mars in this story? Well, Mars is just too small, it's about 10% of the mass of the Earth, to maintain its heat, its interior heat. And because it couldn't maintain the interior heat, it couldn't keep the volcanoes going. So the CO2 there was got converted into limestones, and that was the end of it. Went away forever, and there's nothing left to come out over here, so you lost your atmosphere. So that was a really nice story, but unfortunately it started running into problems. So I'm going to do the Venus problems, but on Mars, you're trying to get a surface temperature that's like freezing or above. And this is the surface pressure here. And these are different solar constants. So if we had a solar constant like the current one, and we had an atmosphere like the Earth's pressure entirely of CO2, we could get up to freezing here. Maybe we need a couple of Mars to do it, a couple of Earth atmospheres to get it to freezing. We don't have the current solar constant. We have 75% of it. You're on one of these lines. So even at 80%, you get up here to a couple of bars, and you're still way below freezing. So you can't get enough CO2 in the atmosphere to make Mars warm. And it's not just that you lack carbon, it's that you hit this curve over here, which is the line where the carbon dioxide will condense out as dry ice. So you basically, you can't just, there's a limit to how much you can shove in because the planet's so cold that the CO2 will freeze out as dry ice and you can't get it. So that was a difficulty here. And there's a whole host of problems here. Fortunately, there's a whole host of problems. We continue to solve this problem. So the first problem here is, where is the limestone? You know, if you're going to have all this carbon dioxide in the ancient past of Mars, it should have made limestone. Where did it go? So there's actually plenty of carbon dioxide there in the dirt. It's all ground up in the dirt. There's plenty there, but you're expecting the white cliffs of Dover somewhere. You're expecting these rivers are going to have massive piles of carbonate, which just haven't been found. So people have said, oh, well, you know, there's a lot of sulfur there, some other reaction prevented the limestone from forming, blah, blah, blah. So this is still a big problem with carbon. Another problem here is rivers are consistent with intermittent flooding. So the geologists who look at these rivers say, well, these are not the Mississippi River. You know, they're not just sitting there flowing all the time. These are like, you know, something you see out in the desert in Arizona or something where it's mostly dry and nothing's happening, and every once in a while there's a big flood. And you get a flood and it goes away, and a couple years later it does it again, and otherwise there's no water there. So this is inconsistent with a picture like this where you have some hundreds of millions of years of nice warm Earth conditions. Why does this matter? This matters because if you want life to arise on Mars like it did on the Earth, apparently a few hundred million years, You'd like to have a nice, warm, wet climate for it to happen in. And, so it's very difficult to have this happen if the rivers are really not flowing under some nice, warm conditions. And it makes it hard to understand where limestone went if it was some long climate that was Earth-like. Another problem here is the carbon dioxide will escape. So again, back there in the back just showed that if you had CO2 that came out of the planet in the first 500 million years, it would just blow off the planet into space. So you're not going to get any CO2 from primordial sources. Maybe if the volcanoes are active after 4 billion years, they can build some up. CO2 escape is a problem. On the Earth, I mentioned there was a problem with carbon dioxide. You need something else, so people are adding methane. There is some methane on Mars, so you might help yourself by adding some methane. But if it turns out on Mars you have to add so much methane that it starts to work against you and cool the planet off. That doesn't work. So in my mind, after 30 years, people have just gone to desperate measures here. So most people now are trying to make sulfur somehow work by making a greenhouse out of sulfur or sulfur dioxide, or making sulfur particles, or I don't know, last year people trying to do with nitrogen oxides. I think that one faded away before it ever got published. So I consider this to be a sign that we either haven't been clever enough to think of something obvious, which is certainly possible, or that the answer is really complicated, or that this just isn't the answer. Okay, so that was Earth parallel number 2. That one, in my mind, doesn't work all that well either. What's the other way to do this? Impacts. Okay, so this is an artist's rendition of an impact which may have occurred early in Mars history and blown away half of the planet, basically. So the northern hemisphere on Mars is like 10 kilometers lower in altitude in the southern hemisphere. And the people who do internal geodynamics say, well, this is really hard to do just with internal geodynamics, so let's just blow it away with a big impact. Really big impact. So this is another idea here that really originated on the Earth. So there wasn't too much activity at impacts. In the 1960s, Harold Urey, a very famous planetary scientist, wrote an article in Science magazine saying all the geologic errors on the Earth ended with a large impact, and that's what caused geologic errors. I don't know if anybody ever read that paper, so it had no effect on the community. And in fact, geologists say, no, this is not uniformitarian. It has to be something slow. It's happening every day. We should be able to go out and see it now, so you can't talk about impacts. So nobody talked about them until the early 1980s when Alvarez group discovered that an asteroid impact probably killed the dinosaurs. So then they became a very popular growth item. And so on the Earth, which was certainly struck 4 billion years ago by numerous objects, hundreds of kilometers in diameter. This impact of a couple of 100-kilometer diameter object on the Earth would vaporize the oceans and heat the crust to some depth to 100 degrees C. There's a fight about whether this would sterilize the planet or not. Most recent work kind of suggests that if you manage to be a bacterium, you're hiding a kilometer below the crust, you could probably not be killed that way. But if you're in the oceans, you're dead by these impacts that happened on the Earth. So what about on Mars? So I already showed you a picture of 100 or some number of craters bigger than 100 kilometers. So we can look at how old are these impacts? How old are the craters? So I have to admit that up until about 6 months ago, I thought something like Hellas was probably 4.5 billion years old, and that there were things on Mars older than 4 billion years or so old. Although there's basically nothing on the Earth that you can find that's older than 4 billion years. So all the Earth's record below 4 billion years ago has been erased. You can find little tiny zircons and things like that, which maybe came from an earlier epoch, but the earlier history is erased. And interestingly enough, so far, nothing on Mars seems to be older than 4.1 billion years old. So these red points here are crater ages, and the blue ones are the rivers. And they didn't date all the craters. This is something like 20 craters that were dated. Here's the river's last flow, and you see these error bars are overlapping, which is in line with statistics. So here's Hellas up here. So Hellas is about 4 billion years old. And these rivers are more like 3.8 or something like that. So Hellas probably didn't cause the last river flow. It's 200 million years before that. I forgot where Isidis is, but Isidis is in some other I think that's Isidis. Yeah, it's too old. Here's Argyre. Argyre, which is a 1,000-kilometer radius object, is sitting right here in the middle of the cluster of all these rivers. And there's a whole bunch of other craters here that haven't been dated, and many that aren't ever going to be dated because they're buried under all kinds of dust. So it's clear that this is the last one to occur, but I'm going to use it as an example here in this talk of what the impact would do. Okay, and there's some other interesting stuff over here, which let's briefly go through. So these are the ages, the geologic ages on Mars. So we have something called the Noachian here, which ended at the time of the last river flows. So this doesn't mean too much. It's something about crater counting. Nevertheless, there's a Hesperian here, the Noachian. Then we have these interesting mineralogy things. So there are clays which are found back in this Noachian era. All the sulfates are formed here at a later time. So the sulfate deposits actually post-date the rivers. So all these people are trying to explain how you're going to make the rivers with sulfur without a problem that they haven't dealt with here, which is that the sulfates came after the rivers. Unfortunately, nobody knows what this boundary is very well. Then we have other things here like the crustal dichotomy, so that big impact that blew off half of Mars, pretty old, older than 4 billion years. There was a magnetic field on Mars. Seemed to have stopped about this time here in the last crater forming episodes. There was rapid erosion. The erosion rates were very rapid back in here. They're so rapid that they're almost like Antarctic erosion rates on the Earth. Some really dry place, so they're not rapid relative to the Earth, but they're orders of magnitude higher than they have been since the last of the rivers formed. So erosion basically ceased on Mars about 3.8 billion years ago. So the punchline of this is that the craters and the rivers are about the same age. Another thing that's unfortunately about the same age are the Tharsis volcanoes. So they have to have an age somewhere in here. And we know that because the Tharsis volcanoes tilted up the Hellas basin. So they have to, this has to be formed after Hellas, which was that biggest crater. On the other hand, a lot of these rivers are flowing down the slopes caused by the Tharsis Tharsis volcanoes. So it has to have stopped, or at least have a lot of its development prior to the age of these rivers. So Tharsis did a lot of its formation in the same time frame. Quite annoying because if it just done it at some other time, it could have just wiped out that whole theory. But I still think the sulfates are going to be in the end to get the greenhouse idea du jour. Okay, so Argyre, which I mentioned, is right at the right age, one of the largest craters on Mars, 1,000 kilometers in diameter. Okay, so you hit the planet, so what? Here's an example of what's called a Rampart crater on Mars. This is kind of unusual because it seems like there's streams running out of it, but they all have this kind of weird-looking muddy flow. So this is just an indication, this is another picture of it, an indication that the ground has got lots of ice in it. And if you have a big enough impact, it's about 20 kilometers across, it could get bigger than the meteor crater in Arizona. If you have a big enough crater, it will penetrate down to the ice. Here's a picture of a crater. There are these fractures going down. So if you fracture the soil down into the ice, you have all this liquid water come streaming out into this ejecta blanket. And if you see these little craters, they didn't do that because they didn't get deep enough to get into the ice underneath the dirt. So there's water in the soil. But, so people know a lot about ejecta blankets because you can see them. very easy to see there's an ejecta blanket. This is what geologists think about ejecta blankets. In fact, if you ever go to the meteor crater in Arizona and you desire to collect part of a meteor, all you have to do is walk over to the edge of the parking lot. And the parking lot's like right here, right at the edge of this ejecta sheet, and you just paw around in the dirt to find all kinds of pieces of the meteor. So these ejecta sheets are easy to identify. But that's not what the main thing that happens in a large impact. So this is some artist's rendition of a fireball that comes from one of these impacts. So when you have a big impactor that's hitting a planet at 10,000 miles an hour, there's an unbelievable amount of energy. For example, the Chicxulub impact that killed the dinosaurs, which is a little bitty 10-kilometer thing, had an energy release that's equivalent to a 1 megaton nuclear weapon every 5 square kilometers over the whole surface of the Earth. So there's a huge amount of energy release here. And that energy is stored as latent heat in vaporized rocks that it hit and the vaporized impactor. So you have this huge amount of energy stored in the vapor, rock vapor. This rises back out into space and then falls back over the planet as hot rock. And we saw this happen, for example, on Jupiter. In fact, apparently we just saw this happen again on Jupiter. Apparently a new impact has been discovered on Jupiter. Too late to see the impact, but to see a little dirty mark on the planet. At any rate, this is the ejecta cloud from one of the Shoemaker-Levy 9 impacts, little bitty thing, and this is just part of the plume coming up out of this thing, this hot plume. It went up tens of thousands of kilometers over Jupiter and fell back down over an area the size of the Earth. Okay, so what happens then? You've got this huge mass of impactor and target material that went into space and fell over the planet. And this is going to deposit hot global ejecta layers. So here's some stuff from the KT boundary layer clay. And so there's a little layer all over the Earth, a few millimeters thick, left of this impact that killed the dinosaurs. And it's full of all these little molten pieces of rock, melt debris from this impact. So we don't know where these layers are on Mars. No geologist has ever gone and tried to even find them, because most geologists haven't thought about this existing. But nevertheless, for example, our gyre should have made a layer somewhere on Mars that's about 40 meters thick. So for reference, this is the edge of the Victoria crater, which the rovers took a picture of. It's about 75 meters deep. So somewhere on Mars, there's a layer from our gyre that's about 40 meters deep. And if you just take the craters, take the 20 dated craters I showed you ages on, they're 700 meters thick of ejecta layers from those things over the planet. Almost a kilometer of ejecta debris has fallen on the planet. When this stuff falls on the planet, it's probably like 2,000 degrees centigrade hot. So this is basically over the entire planet. You're sticking 40 meters from our gyre of dirt that's 2,000 degrees hot. So this certainly has the potential to melt quite a lot of water. How much water might you melt? So there's three simple sources of water here. So one of them is the impactor's got water in it, and will certainly be released. The other one is the ground has got water in it. I've shown you there's lots of water there. And of course, if you put a 2,000 degree hot layer of rock on top of an ice cap at the poles, it's going to melt all that stuff. So if you just take those into account, you expect our gyre to produce about 10 meters of water over about 5 years. So these are very short-lived events. You get intense rainfall, meaning a rainfall rate like the Earth has now, a couple meters per year. So the average rainfall rate in the Earth is about 1 meter per year. We get about half a meter in the southwestern United States, about 2 meters a year in the Amazon jungles. So you get about 2 meters a year over 5 years or something. How much is that? Well, here's a French frigate about to get hit by a 15-meter high wave. So you get some idea of the depth of this. So we're talking about the entire planet over 5 years, and you're picking up the depth of water, something like that, which is an awful lot of water to pile planet. It's going to go somewhere. It's certainly going to pond up and form rivers and lakes. And, so, unlike the greenhouse, for which there is no evidence of CO2 ever being prevalent on the planet, there's no evidence of sulfur ever being in the atmosphere. There's no evidence of methane ever being abundant. There's no evidence that the Tharsis volcano ever even emitted CO2, which is actually somewhat surprising to think it would, because it's not reprocessing regularly. Unlike that, we know that there are craters on Mars. We know how big the objects were that hit them pretty much. And the energy released there is going to definitely do something. In my mind, we're a lot further along in this theory, despite the fact that I'm practically the only person in the world who works on it. But we are in the other theory, which is like 30 years trying to make it work too. But there are people who complained about this. So Bruce Chakosky, who speaking I think in 2 months or whatever the next talks on this is. Mike Mellon in 2004 wrote, they were criticizing all the other ideas for making Mars warm. And they said the impact hypothesis has its own problems, meaning all the others have problems too. However, especially regarding the relative timing of impact events and erosion events typically associated with the Martian climate change. So what they meant is they thought Hellas was 4.5 billion years old and was just too old to have anything to do with rivers. However, this has been solved, and just showed you the crater river dating. Argyre is right in the middle of the last flow of water of the rivers. And so this problem has been eliminated. So here's another problem, which is a pretty interesting study that hard to understand exactly what they did, but so they have made a model of water flow in rivers using an arid region like the American Southwest as a numerical example, and they let it rain in their model, and water flowed down a bunch of rivers and eroded them, and some of these rivers flow into craters and breach them. And so what they say is the paucity of crater exit breaches, so they're just studying one little place on Mars, which actually happens to be younger than almost all the other rivers. But nevertheless, in that one place, they don't see the craters being breached, which means that the water flowed into the crater, but it didn't pond up high enough to flow out. So because they didn't pond up high enough to flow out, I think that episodes of nearly constant deluge style, which means average rainfall of the Earth, precipitation for several years won't work. But the answer to that is, well, there's plenty of other places on the planet where the craters were breached. So here's a crater that Tafasik had studied, and there's a little river up here coming in, and there's another one over here coming out, right up here. And if you look at the topography of this crater, which is down here, point A is up high, and this other point over here is down low. So evidently the water flowed in here, and it filled this thing up until it got that high, and then it spilled out over the other side. So there are places where there are crater breaches. And so this is really an interesting idea. And these people thought that it would take 11 to 18 years at 2 meter per year precipitation rates to do this, which I just showed you was exactly the precipitation rate and duration kind of thing you'd expect from Argyre. However, they said, oh, this couldn't possibly happen. It must have really taken 500,000 years to make this. And so they rejected this hypothesis because they just couldn't figure out how to make that much rain. Okay, here's another interesting example on the Earth of how you can form something suddenly. So the Colorado River, which runs down through Southern California on its way to Mexico, looked like a good thing in the early 1900s to take water out of and make the desert bloom with irrigation schemes. And so someone was starting to work on that and made a mistake and cut a big hole in the Colorado River. The entire river was diverted for 2 years and flowed into Southern California, where it made the Salton Sea, which is a large inland sea. And this is a picture taken from the early 1900s. So what happened in 9 months was we opened up this thing, and in 9 months, so this is a waterfall. And this waterfall is moving backwards at 1 foot per minute. You know, so that's the rate at which this thing is eroding this channel back from the Colorado River being diverted. And so it formed a 70-kilometer long channel in 9 months. And that's the average length of the rivers on Mars, is 70 kilometers. So it's clearly possible to have some sort of a flood like this and make yourself a river of the type seen on Mars in a short period of time. Okay, so what we got left to think about here. One thing is to think about how to get anybody else to work with this problem. So one question here is, you know, is that the end of the story, just to have this sudden deluge? Probably not. But probably with water recycles, there's probably some greenhouse effect from all the water. There could be small impacts that do little things. We don't know what any of that does. This water, we're creating a steam atmosphere here that's hundreds of degrees and is cooling off. And when it gets cold enough, the water comes pouring out. It's probably pouring out at 100 degrees centigrade on the ground. So this is not a terrestrial kind of river. This is erosion that's occurring from 100 degrees centigrade water falling on ejecta sheets that have just been put down by the impact. So you put down a 40-meter thick ejecta sheet, which is obviously not very well consolidated, and then you dump 100 degrees centigrade or more water on it. Who knows what that does? This crater breaching thing is interesting because some places are breached and some places are not. What does that mean? There must be some information there. And it'd be really nice if you just tell how long it took a river valley to form. So the geological community is all convinced that this is a 100,000-year process and all the rivers took 100,000 years to form. But you know, it's very hard to feel any confidence in the way they deduce that. You just sort of look at the picture and it looked like that took a long time, so it took 100,000 years. So like the crater breaching people say, well, I can only fill that crater up at a certain rate to keep it from breaching, and if I fill it that way, then I have to do it 500,000 times to make enough material be removed to make the river. And I'd like to end here, and then we'll get right to your questions. So we're almost out. Okay, what's the summary? Large impacts are contemporaneous with river formation. The river bars are overlapping, and the jar is right in the middle of it. We know there are sources of water here just beneath the surface because we can see these Rampart craters, lots of other things that tell us there's buried water there. We know that there are hot ejecta layers generated from large impacts. We saw just this thing happen on Jupiter, a pretty small impact. And we know that lots of rainfall can be created from the steam atmosphere of the ejecta layer. You don't have to worry about making this hot. A huge amount of energy is going to go into the atmosphere at 1,000 degrees centigrade, cool off, and come out as very hot water. And there's lots of